Let's see now. We were talking about, let's see, we were talking about entropy. I talked about that entropy can never decrease in an isolated system. And then I gave an example of where entropy did definitely decrease. But then I pointed out that, and it was that example with freezing a glass of water. And I pointed out that in the scenario that I set up, putting the glass of water in a freezer, basically, that glass of water by itself was no longer an isolated system, and so you couldn't expect the second law of thermodynamics to apply. But then I said, if you correctly define your system to be not only the glass of water, but also the freezer itself, and also the air that you suck in from outside and then dump out back, the hotter air now back out into the atmosphere. If you add all of those things together, make that your system, now you have an isolated system, and there the entropy of that system strictly increases, or at the very best possibility, simply remains zero. In that particular scenario, by the way, it could be shown that the entropy will definitely increase. Okay, so that's fine, and I did some examples with expanding a container of gas, and that was a few lectures ago, a few recordings ago, and I threw in some terms. I said, oh, well, we're going to expand the gas, and we're going to expand it isothermally. I said what isothermally meant at the same temperature, an unchanging temperature, and I talked about heat flowing into the gas and heat flowing out of the gas and all sorts of things. Let's talk about gas. So let's take a step back and remember what I talked about thermal energy. And I said thermal energy is the result of the fact that the particles that make up a macroscopic object are all moving. They all have kinetic energy. And so the thermal energy is a measure of the kinetic energy, or I should say, I'm sorry, the thermal energy is a consequence of the kinetic energy of the particles. Well, there's a couple of things. First of all, as I've already pointed out, we cannot possibly determine the kinetic energy of each and every one of the particles. The best we can do is talk about the average kinetic energy of the particles, and which would require knowledge of the average masses and of the average velocities, or any of the average speeds of the particles, and that's something we may talk about. But I want to take a different tack here and remind you that I said, as a replacement for thinking about kinetic energy, we instead invented the concept of temperature. And so now I say that the thermal energy of a system of particles, in this case, our system particle will be a system of gas particles. Anyway, the thermal energy is directly related to the temperature of the object. So let's now, finally, I've been hinting that we would do this. Now let's finally take that and run with it. Okay, so I've said, so putting mathematical expressions to this, pin that I like here, that the thermal energy is proportional to the temperature of the gas, and that's just more or less by definition of temperature. Temperature is defined so that thermal energy is in fact linearly proportional to it. Okay, so far. But then too, it seems like the amount of thermal energy in a container of gas should depend on, well, the number of particles of gas you have. If you have one particle, even if it's moving really fast, it can only have so much kinetic energy, and therefore your container of one particle of gas can have only so much energy, thermal energy. If you put a second identical atom, or identical gas particle, in the container, you have then, doubled the amount of thermal energy in your system. So, in short, the thermal energy should also be proportional to the number of particles that you have. So capital M, just the number of particles of gas. The next number that I'm going to throw in there is less obvious, so I'm just going to give you a hand-waving argument and ask you to trust me on this. We've already said that the thermal energy is related to the kinetic energy, and you know how to calculate kinetic energy, 1/2 mv squared. So it's going to turn out that a factor of 1/2 is going to appear in the equation that I'm developing here. Okay, and that 1/2 comes from the same place where the 1/2 n comes from in 1/2 mv squared. Now, you may or may not know where that 1/2 comes from, and it hardly matters at this point. We'll just sort of accept that it's the case. But in addition to that, well, actually, let me take a different tack. Okay, so the thermal energy is proportional to both of these things, and therefore it is proportional to the product of these things. Okay, and so now we're at the point where we need a proportionality constant. Well, it turns out the proportionality constant is written in sort of an unusual way. And it's a consequence of the history of the development of the thermodynamics of the science. The result turns out to be, and I'm going to write this down in sort of bits and pieces here. Well, first of all, so this stuff here inside these square brackets is the constant, or a collection of constants actually, that I'm about to describe for you. So n times t is out here. Okay. First of all, I'm going to have the 1/2. Okay, that I was just talking about. The next thing I'm going to put here, I'm going to shift this a little bit, is there's another proportionality. Now let me do this in reverse. However, the kinetic energy of a particle is due to, of course, its motion in space, its velocity in space. But of course, if you think about it, the particle can move in 3 directions. In the x direction, in the y direction, or in the z direction. Okay, and so in principle, at any instant, it can have has a velocity vector that has all 3 components in it, and so all three components, each of the 3 components of the velocity vector will contribute to the kinetic energy, and so for that reason, we pick up a factor of 3 out here. Okay, and then finally, the actual real proportionality constant was developed and derived by a guy named Boltzmann. And so this constant is labeled K sub B in his honor. This K sub B is Boltzmann's constant. And its numeric value is 1.38 times 10 to the minus 23rd joules per Kelvin, Boltzmann's constant. Boltzmann, yeah. Okay, and so writing this a little more coherently then, the relationship that we're after, how is the thermal energy in a container of, in this case, gas, related to its temperature? The answer is 3/2, in the way it's traditionally written, n times K sub B times T. Okay. As a side note, I don't particularly like the traditional way of writing it, because to me, n is a number that you control, where K sub B is a constant, but whatever. Go talk to a brick wall, right? Anyway, so there we go. So that's the relationship that I was after. So far, so good. Yeah. And, you know, you could plug in some numbers, and it's not terribly difficult. So if I have, you know, if I have 10 trillion gas molecules, right, and then Avogadro's number, I'm sorry, I'm getting ahead of myself there. Sorry, Boltzmann's constant is just that value, and then you say it's at 373 degrees Kelvin, so that's 100 degrees Celsius, right? Pretty hot. Then it would have a lot of thermal energy. You just plug those numbers in. The difficulty, though, with all of that was knowing how many particles you have. I mean, if you look at an average balloon or something that's filled with air molecules, you inflated it, right? How many? You have no idea how many atoms there are in there. And this actually, in the history of thermodynamics, was a rather vexing problem. And people were trying to figure out How could you know how many particles of gas you had in a container? And the problem is not simple, and the details of how it was solved is very interesting, but I'm not going to take the time here to discuss it. Perhaps we can talk about it in class, but in any case, the answer that was eventually came to involved a number and a new definition of a physical quantity. The physical quantity in question so let's see. So the problem that we're dealing with is that it's hard to determine the value of n. So how can we either figure out what n is, or if we can't figure out n, can we rearrange this expression and express it in terms of some other physical quantities that maybe is easier to figure out? And the answer is, yeah, of course it is. And so here's the first concept that we need in order to accomplish that goal. We're going to define something, and we're going to call it the quantity of a substance. That's the official name. In human terms, this is how much of it you have, okay? But it's expressed in terms of a unit that's known a new unit, an SI unit. Of the mole. You've probably heard of this. Now, this is not the small burrowing mammal. You'll notice it's just MOL. No, this is short for molecular because again, it's the roots and history of the science, and it's not important here. But molecular mass is the essentially. So it got shortened to just the mole. So when I ask how much quantity of gas do I have, I will answer the question in terms of some number of moles, some amount of moles, some number of moles. Okay, rather than saying some amount of kilograms or some number of particles or whatever, I'll just say some number of moles of gas. Okay, and so we need to know what the definition of mole is, and that's not terribly difficult either. A mole is defined to be, so 1 mole of a substance, I should say, this is a very complicated definition, so I'm going to write it out and then I'll talk about it. 1 mole of a substance is defined as 1 mole of substance has the same number of particles as there are in, get this, 12 grams exactly of carbon-12. Okay, that needs some explanation. I'm going to assume a whole bunch of knowledge here. If you have any gaps in this knowledge that I'm assuming, obviously do talk to me. But, so carbon-12, 6 protons and 6 neutrons. So if I have 12 grams of it, so I have a little pile of carbon dust sitting on my scale, and I measure out 12 grams of it, then there's some number of carbon atoms in that little pile of dust that I've got on my scale. however many number of particles, however many atoms of carbon-12 I have, that's some number, and you might already know what that number is, but whatever, it's some number. And in theory, I could count with tiny little tweezers and a big magnifying glass. I could count how many atoms I have in my little pile of carbon dust that has this mass of 12 grams. Whatever that number is, then any substance that has that same number of particles, no matter what the substance is defined to be 1 mole of that substance. So one consequence of this definition, by the way, I want to say this really early in it, is that 1 mole of oxygen and 1 mole of carbon do not have the same mass. They have the same number of particles, but they don't have the same mass. For that matter, 1 mole of carbon and 1 mole of bricks have the same number of particles, same number of bricks, same number of atoms, vastly different masses, though. Okay, so please understand that saying that two things have the same number of moles does not imply that they have the same mass. Okay, so please be aware of that. Right, so it's just a number, and you probably have heard what this number is, and actually experimentally determining what that number was not simple, but it was done eventually. (6.022 times 10 to the 23rd). And I'm going to write the units here. And I'm going to write them in a very peculiar way. No, okay. No, I think I just want to say that. So there's no, yeah. So this is the number of particles, okay? And so we talk 6.022. This number was first suggested by the Italian physicist Avogadro. I'm going to pause the recording for a second. Somebody's coming in. All right, sorry about that. The cleaning people came in to clean, so yay, we have a clean room now. Okay, the number of particles in 12 grams of carbon-12, and it's not a coincidence, by the way, that it's 12 grams of carbon-12. Anyway, turns out to be 6.023, and so we say one mole of substance, of whatever substance you have, has 6.022 times 10 to the 23rd particles, or we can talk about the number of particles per mole. Particles? Yeah, okay. Okay. This number, as I was starting to say, was named in honor of the Italian physicist who first put forth this idea, Amedeo Avogadro. Avogadro's number. It's, as a matter of science history, by the way, it should be mentioned that Avogadro himself only suggested this idea as a concept, as a useful number to have for the purposes that we're going to do. He did not himself actually determine what that number was. It was left for the French physicist Jean Perrin some years later to actually determine the value of Avogadro's number, and for that and related work, Perrin got the Nobel Prize in Physics. So yay for him. Okay, so that's Avogadro's number, and so we will find this useful. Now, this recording has gone on too long, but really I just have a few more concepts to get across, and so, hit the pause button if you're getting tired. Okay, with this definition, I can then say that I just changed my mind, and let's do another recording.